Start recording. So we did some reviews already. So let's continue along the line there. Okay. I think what we did is a dot product at the end of the previous lecture. So if you don't mind, I'm going to maybe finish the lecture just a few minutes, just make sure we have enough 50 minutes covered for each lecture. Because I don't think there's anybody after our lecture. If you have two vectors, A and B, forgive me for my handwriting, this half arrow, okay, this doesn't look like a half arrow. So on top of the letter A and B here, they are half arrow. Right? Sometimes you use a full arrow, but they are half arrow. So A1, A2, A3, B, B1, B2, B3. Right. Okay. So we presented A dot B. There are two formulas, right? But I'm going to present the second one here. The second formula is A, B, and cosine theta. So this is A, this is B, theta. Good. And then, in particular, I didn't start this part here. And there's an application of dot product. We call it a vector projection. This relates to one of the questions asked by a student at the end of the last lecture. You know, what is the meaning of dot product? Right? So this actually, to some extent, will give you some idea the actual physical meaning behind the dot product. So here's the formulation of the problem here. Okay, so let's say if I have a vector A at here and a vector B. So that's given conditions. Now if I ask a question, okay, the question here is, so if we project the vector A, so basically you're doing projection of A onto the direction given by B. So if we want to do this, right, so what this means is, if I explain it here, so basically projection you learn in CAD, you draw a perpendicular line to that direction, right? You do the projection, 90 degree. So you do a 90 degree at here. And also, by the way, because I'm drawing on the a computer screen, right? So it looks like a 2D, but in reality, I mean, 2A and B in 3D can be in any configurations. But you always do a 90 degree projection here, right? So that's 90 degree, and then from here to here, this red one is what we call the projection of A onto the direction given by B. Okay. So that's the question here. So the question basically is, what's the red part, right? How do I find the red arrow here, the red vector? You know, when you project A into B, you still get a vector. So how do I calculate this new vector at here? So let's do it, and while we're doing it, I will figure out some meanings of a dot product. I'm going to use this symbol here. I'm projecting A onto the B direction, right? Onto the direction given by B, right? Now, if you recall before we write it here, in the previous lecture, we covered a simple concept called univector, right? And we also specifically have mentioned that univector will be used for what? For the direction. So every vector has two components, length and direction. The direction information is given by the univector of itself, right, of the vector itself. Okay. So if I'm saying onto the direction given by B, essentially I actually can use the B hat. Okay. So B hat representing the direction given by this B vector. Okay. So of course B hat is univector. You know, you can draw B hat Okay, anywhere, just free, just to indicate that is the direction of B. So this symbol here basically represents the projection of A onto the direction given by B or onto the direction B hat. Okay, so that's the formulation. Now we just have to figure out what is this term, right? What this term is. I'm going to strictly stick to the definition of vector concept. The concept vector has two information, right? Definition: length and direction. Right? Length and direction. So you want to look for a vector, then you need to look for its magnitude and also look for its direction. So let's figure out each component at here. Let's figure out the direction first. Okay? Direction is the easy one. What is the direction here for the red one we're looking for? What direction is it? Yes. Sorry, come again? Direction to the right. Use the math symbol. That's right? No. Use what I have on the paper, the math symbol. B hat. Excellent. Yeah. I mean, to the right, to whose right, right? Yeah, so you have to be very precise. That's all about math. So let's use a symbol. That's B hat. Exactly, right? B hat is the direction. Okay, now let's figure out the length. Okay, figure out the length here. So I'll give you one more symbol here. Let's say the angle between the two vectors is theta. What is the direction? Oh, sorry. What is the length of the projection? At the length of the projection here. Can you write it down? Yes. A cos theta. Yes. If I see it more properly, I will see magnitude of A times cosine theta, right? Excellent. So magnitude of A, this is the symbol I use, and then times cosine theta. Good. So that gives us the length of the projection. And this gives us the direction of the projection. So together, we get the projection of A onto B. Now the only thing is, right now, let's do a little bit a simplification in here, because I have a mixture of vector and then theta. So I want to get rid of everything just to use only the vector information, okay? Yeah. So here is, it's a little louder here, right? Yeah. So here's the way I'm going to replace the cosine theta with the known condition, which is exactly this formula that we have used from previous lecture. So I'm going to replace the cosine theta based on this formula. Essentially, cosine theta equal to A dot B divided by the multiplication of the two magnitudes. So then now I'm going to use that. So A dot B divided by the multiplication of the two magnitudes. Okay, this is what's in the bracket. This is what's outside the bracket. Good? So up to here, we can further simplify it, right? So you look at the way it's written here. Obviously, you can cancel these two terms because they're the same. Yeah. So what you're left with, right, is you have A here. Okay, you have an A here, then dot this B over its magnitude. This is what's in the bracket, and then B hat. So far, so good? Good. I can simplify one more step. What is B vector over its magnitude? Another B hat, exactly, right? So you got A dot B hat. So that's probably as far as we can go, right, in terms of derivation here. So basically, a little bit too far now. Let's rewrite this projection of A in the B hat direction is represented by this formula here. Okay. So you might wonder, what's so special about this? So now let's delve a little bit into this again, right? And then you'll see the whole meanings of my doing this purpose here. So first of all, let's get back to the essentials of a vector definition. Remember, vector definition is length times direction. So always remember this, right? So now you can clearly see, right? You can clearly see that in this current example, the length is represented by A dot B. Right? So the length that here is A dot B. And A dot B, if I have to see it in a very precise description, then I will say this is the length of the projected vector. Okay? The projected vector from A to B hat direction. So if you see it precisely, right, A dot B hat give you the length of the projected vector from vector A, to the direction given by B hat. So essentially, if we come back to the question, so what is dot product? Right? This is one way to interpret dot product. When you have a vector and you use it to dot a unit vector, now you should be able to firmly remember what that vector dot unit vector will give you is the length of the projection, right, from this vector to the unit vector direction. Good? Yeah. So so let me ask a question, very quick question. If I do the Zoom, I'll do a multiple choice, but here I'm going to ask you to raise your hands. Okay? So the question here is, let's say, so I'm going into a 3D space. Okay? So X, Y, Z. So suppose this is a vector PQ here. Okay? And then in the 3D space, there's a direction given by U hat. Okay? So now my question will be, if I do PQ dot U hat, if I do a PQ dot U hat, what does it give it to me? Projected vector in the direction of U hat. Okay, that's A here. B, length of the projected vector. Okay, in the direction of U hat. Okay, so there's only two choices here. So either A or B. Okay, give you maybe 5 seconds here to read it through and write it down. Yes. So he answered A. Anybody? Let me see the hands. Who would pick A? A few hands. Who would pick B? Majority? Yeah, majority wins this time. So this is a tricky part. So you have to firmly remember, right? So this is the length. And first of all, dot product doesn't give you a vector. Dot product gives you a scalar quantity. So it should give you the length of projected vector in the direction that you have. This is a particular useful formula, actually, because later you'll see we need to find sometimes the length of a certain quantity. Okay? How do I find the length? You can try to figure out, maybe use a vector and then dot the other direction, in that direction to find the length. Okay? But this has to be, remember, this has to be a unit vector. Only when this is a unit vector, you can make a conclusion, okay, as a B at here. All good? So we'll see where we can use this shortly in the next week's lecture. Okay, this is basically an application of the dot product. Any questions so far? Yes. It is a scalar. Second part? What's the second part of the question? Yes, it is. We have specified the direction. So graphically, what it looks like is this. So when I say the projection PQ in the U-hat direction, right? So basically, you drop a line like this, 90 degree, right? And then you get your projected vector, the black one. And then you also have the length representing that black vector. So the length of this black vector here is PQ dot U hat. Right? So of course, length itself doesn't really associate with the direction, but in this case, we know it's associated with the vector, which is represented by a certain direction. Yeah. Very good. Okay. All good. All right. So that's dot product. Okay. The next important product is called cross product. Okay. Again, let's start from the simple formula first, okay, and then we'll see how cross product actually will lead us into certain kind of concept applications. So assuming we have the same two vectors given, A and B. So when you have two vectors given, then it is obviously, you can always move the two vectors to touch each other, right? Start from the same location. And also two vectors are like two lines, as we're going to learn. When you move the two vectors together, and that will uniquely determine a plane, which actually will come to that in Monday's lecture. So it's pretty obvious, right? When you put the two vectors together, there will be a plane goes through this vector. Actually, a unique plane. You're not going to have two planes going through the same two vectors. Right? So that's why I'm drawing here, supposing 3D a plane containing this A and B vectors. So then A cross B, by its definition or by its formula, it's written as this. It's written as this. So first for A and B, we know what they are. Theta is the angle between the two vectors. Now n at here, right? N here represents a vector, univector, that's normal to the plane, which contains the A vector and B vector. Okay, so that n here, it's a univector perpendicular to the plane, going through A and B. Right, that's what n is. So now you look at this formula here, then again related back to the definition of a vector. So the one in the bracket is basically the length. And then the one outside here is the direction. Okay. So that immediately tells us dot product produces a vector. That's fundamentally different from dot product, right? Yeah, cross product gives us a vector. And the length of the vector is this. And the direction of the vector is a direction normal to a plane containing A and B. So graphically, right, basically you can always represent this A cross B like that. So you can draw a vector A cross B. Doesn't really have to draw here because it's vector free, but just for illustration, you can draw it, share the same initial point. Apparently, A cross B is perpendicular to the plane, which means A cross B also perpendicular to what? To the A or B. Okay? So because it's perpendicular to the plane. Yeah. Any questions? Okay, good. So in your first year, you must have learned how do I find the proper direction of A cross B? So what is that? The right-hand rule, right? So you cross your hand from A to B, and then the thumb points the direction A cross B. That's right-hand rule. And if A, B reverse their relative location, right, then maybe A cross B is the other way around. Right? Okay. So this is sometimes we call it geometric formula for cross product. Okay. Now, alternatively, you can also calculate your cross product using the following formula here. This is basically using matrix formula. We have the first row, I hat, G hat, K hat. I'll explain what they are. The second row here is the component for vector A. The third row is the component for vector B. Okay. So what's I hat, K hat, J hat? So this is a time I can maybe introduce another notation that we use to represent a vector in 3D space. If this is the coordinates for a 3D space, then each one of the axes, x, y, z, you can find a unit vector representing its direction. So I hat, J hat, K hat, basically the unit vectors for each axis of the Cartesian coordinate. Okay. So then later you're going to see, for example, right, the original A vector, A1, A2, A3, okay, which is the way I've introduced the writing introduced from previous lecture. Half angle in between, you have the basically the coordinates or the components of the vector. So alternatively now, you can also write this particular vector using this notation. Okay? So A1 I hat, A2 G hat, and then A3 K hat. So they are equivalent. Sometimes you'll see both of these type of notation in my lecture notes. Good. So coming back to the matrix here. So this symbol here basically this is a determinant. Okay, so this absolute sign here represents a determinant. So we're trying to calculate the determinant of this 3×3 matrix. You learned in 179 very well in terms of how to calculate a 3×3 matrix determinant. The results, okay, of the determinant is, so let me write it a little further here. You get A2 B3 minus A3 B2 I hat, and then minus A1 B3 minus A3 B1 G hat plus A1 B2 minus A2 B1 K hat. Okay. So this is the results of the determinant of this 3×3 matrix. So essentially, if you have the vector AB, then you can calculate its cross product using this way. Okay. Now, this is actually a very important step to do in many, many questions that you will solve. A very common mistake is the middle term. In the middle term, some student can flip the sign. So the way I write in here, I have a negative, this term minus this, the bracket. Now sometimes, if you move the negative sign into the bracket, right, they become a plus, but they become this term minus this term. Right? It's the same thing, right? Yeah. But don't confuse yourself. Right? You have to be consistent in terms of how cross products calculated using this formula. What I recommend is just spend 1 minute, no more than 1 minute. You write this formula maybe for 5 times, and it should be yours, at least for this term. Right? If 1 minute is not enough, just spend another minute to write another 5 times. Okay? Yeah. It's not the smartest way to do, but it's an efficient way to memorize this formula. But of course, if you to jog your mind for 179, the way we always calculate, there's a formula, right, to calculate multi-dimension determinant of multi-dimension matrices. Okay. So in terms of formula-wise of cross product, there's not too much. This is basically that's it, right? I would recommend this one to be permanently remembered. Okay? So then the question here is always, where do I see cross product? What are some of the meanings behind the cross product? It's just like a dot product, right? So we're going to be able to see some of this in the next 2 examples. Okay? I will call it example, or maybe just let's call it applications or something like that. Okay? So number 1, okay, let's look at the quick application is how do we calculate the area of a parallelogram? So area of a parallelogram. A parallelogram is a geometry basically have 4 sides. And that's a parallelogram. Now this time I'm forming this parallelogram using 2 vectors. So let's say this is a vector A and this is a vector B. And they are sandwiched by an angle theta. So we're trying to get the area. Of course, you can always say, okay, the area of parallelogram, I know that, right? We learned that in high school geometry. It should be pretty straightforward to calculate, even if we don't know vector. But now this time, I'm going to relate the area of the parallelogram to the vector here, okay? To the vector A and B. But we start from the very basic formula for area of a parallelogram. And that basically is you use the bottom length. Right? You use the bottom length of the parallelogram, then multiply by its height. Right? That'll give you the area. So then from here, we dive into detail. How do I find the bottom length? How do I find the height? So let's do that. First, let's find the height first, maybe. Right? Or maybe let's find the bottom length first. Now, that's pretty easy. Right? Because bottom length is given by the length of the vector A. So your bottom length basically is the magnitude of the vector A. That gives you bottom length. And the height, right, which basically represents the vertical difference between a perpendicular vertical difference between the top and the bottom sides, which is the height. Okay? Now, in order to get the height, I make use of what I have here. Right? I can move the height over here. Right? This is also the height. So if I want to make use of all the symbols within this picture, here is the right triangle. And you have the sides of this, the Pythagorean, the triangle, right triangle, and then you also have the theta here. So the height h, if you want to express h using this side, the length of this side, and the theta, and what would that be? Exactly, right? So the length of the side, which is the b, that magnitude, times sine theta. Okay. So that gives you the bottom length, that gives you the height. Okay, that's it. Okay. And then from here, okay, I'm going to go back a little bit, right? The area equal to absolute A times absolute B and then times sine theta. And what is that, right? So let's go back a little bit here. Right? And this is a part of the formula for calculating A cross B. In this part of the formula, we call this is the length of what? Of this cross product, right? So basically, what I'm getting here is I'm getting the length of the cross product. And that's it. So essentially, you have a connection between part of the cross product, not the whole cross product, right? But there's cross product related here. So the magnitude of a cross product will actually give you the area formed by these two, the area of the parallelogram formed by these two vectors. That's one application. In some cases, really depends on the angle here. Now, this angle is an acute angle. If the angle is a dull angle, then this length will probably give you a negative. So sometimes, because we are looking for area, so you can put an absolute sign here. So you basically, whatever value you get, just get rid of the negative value, then you get the area. Okay? Yeah. So that's an example how you can make use of this cross product. We actually will make use of this formula right away, maybe not today, or maybe I could start a little bit, when we derive the plane equations, the plane equation in 3D space. Right? Any question on this simple example? Good, all right. So second example, I need this example for my next lecture, so they're all connected, okay, is how do I calculate the volume of a so-called parallelepiped? Okay. The volume of parallelepiped. So what this means is, I'll draw it right away here. Okay. So let's suppose I have three vectors this time. A, B, and C. And I'm going to place the three vectors, okay? So move them around until they all touch each other from a single starting point. So then, let's say if this is a B at here, so let's draw this a little bigger. If this is a B here, and this is a C, okay. And then let's draw the A. I use red color. It's right over here. And to make you show it a little bit better here, so essentially suppose that the B and the C vectors, okay, they're in this plane, and A is somewhere, outside the plane. Okay, so they're not in the same plane. If they're in the same plane, actually, we're not going to be able to get a volume. So this is the relationship between A, B, C. Then I can now create a 3D object using the three vectors at here. So this is very straightforward. So at the bottom here, you can create a parallelogram using the two vector B and C. And then you keep doing for the other sides. Bottom line is, at the end, when you sketch out all sides, you got to incline essentially like a box. And this geometry here is called a parallelepiped. Right? And now we're trying to find its volume using the given conditions, which are the values of A, B, C vectors. Right? So that's the idea. Okay? Okay, so again, this is not a simple just geometry. We need to we're now making use of the given ABC vector to derive the formula, all right? But I will start from the very basic definition for volume of a parallelepiped. So when you have a parallelepiped, and if you want to find its volume, the basic formula is you need to find the base area first, and then you multiply by its height, So if you can find these two values, you multiply, and then you get total height. So that's the formula for parallelepiped. It's different from, this is for this formula. If you look at my lecture notes, of course, not all geometry, 3D geometry has the same formula, right? Okay. So now we start from here, and let's figure out what is the base area and what is the height. And we'll figure it out by using ABC vectors here. Base area, in this case here, let's, you literally you can choose there how many sides? 6 sides here, right? You can pick each side as a base area. But this time, I'm going to pick this side, the bottom side, as this is my base area. Okay? So B and C. Base area, this is what? This is a parallelogram, right? So what would be the base area? Excellent, right? That's exactly what the problem we just solved there, right? So the base area is magnitude of B cross C. That's the area of the parallelogram. Okay, that's easy. So now it's a height. This one probably would have to take a little bit of writing at it here. So height means you draw a perpendicular line between the top and the bottom surface, right? And this is your height. Okay, that's what we need to find out. So the question essentially is, how do I find the height at here, right? Using all of the known vectors, right, in this case. Still, we're going to try to make use of everything that we have reviewed, and even the conclusion, some of the results of the examples here. Okay, yeah. So how can I find the height at here, right? So let me give you a hint first, and then we'll slowly be able to get the results. Okay. So let's suppose this is a plane containing vector BC. Okay. So I'm going to give us a temporary vector. Let's call it n hat. And n hat, the same definition as when I was introducing the cross product. So n hat is a unit vector perpendicular to the plane formed by B and C. All right? Yeah. So n hat is a free vector. You can move it anywhere you want. All right? You can move it anywhere you want. So now, can somebody actively think, how do I find this height h using n hat and a vector? Yes? Exactly. Project A onto the n hat. So, what's the formula for project A onto the A hat? So precisely, I shouldn't say, you want to see precisely, right? You want to see precisely, as I have just listed, it should be the length of the projection. Okay? So how do I get the length of the projection of A onto n hat? Using an exact, yes? Yes. What dot what? Absolutely, right? A dot n hat. There. So if I give you temporarily the symbol n hat, then you can get the height with the application of A dot n hat. Good? Excellent. So, of course, you don't want to keep the n hat here, right? Because that has nothing to do, because, with ABC. We want to use everything, transform everything into ABC. Okay. So, let's see how we can get n hat. Okay. So, n hat, we know exactly what n hat is. N hat is a unit vector normal to the plane. So what would be an alternative expression for n hat? A cross B? Not A cross B, I mean, B cross C. But B cross C is not n hat. You had to what? If I just write B cross C, is that n hat? Magnitude of it. So how do I get the magnitude of it? a magnitude of it? Is that magnitude of A? No, not a magnitude of A hat. So how do I get n hat? So we know exactly n hat B cross C is the same direction. But how do I get the n hat? Yeah, Colin. Excellent. Yeah, that's right. Right. So you have to normalize it to get n hat. Okay. So now I have my n hat, which is B cross C divided by its magnitude. So they're kind of step by step, and you're introducing the known conditions A, B, C. By far, by this stage, you have everything made use of. Right? You don't have to go any further. But now you can simplify. You see, this and this cancel each other. Right? So you end up with A dot B cross C as a final result. So that's the volume of the parallel piping formed by the three vectors A, B, C. So this one here involves both dot product and cross product. Good? As a matter of fact, I'm not going to show the details at it here. We can show that there's a connection between this formula and the linear algebra. Is that this A dot B cross C, is this formula here, is basically the determinant of the 3 by 3 matrix with each row given by the vector ABC. So they're very nicely connected at here. If you want to show it yourself, you can calculate this, no problem at all. Okay, so it's not that big deal, but it's just a little bit computationally cumbersome. Now remember, for this A dot B cross C, I used a base area formed by B and C. And I did mention that, I mean, the parallel pipette has 6 areas here, right? So you could choose another area as a base area. So let's say if you choose AB side as a base area, or you choose AC side as a base area, then you get slightly different formula other than this one here. So basically what you're going to get, for example, B dot A cross C, or C dot A cross B. If you choose different base area and you follow the same procedure, you get this formula. The calculation will all give you the same results though. Okay, so I think that sort of concludes the review here. You know, this is the dot product carve-up. A little bit new maybe in terms of the applications here, how we introduce the dot, but not just give you the formula, right? The important thing is actually we're going to try to make use of the results from here and also from here for our next stage of calculation. Okay, yeah. And one of the thing we're going to probably come back several times is the meaning. You know, when you have a vector dot, a unit vector, and we use that in quite a few places, right, the concept. You get the length of the projection, right? So always remember, you get the length of the projection. Okay, good. So I still have a few minutes, so I think we can start the question. I'm not going to be able to solve the whole question, but we can start the question. So this is next topic here is we're getting into really the content of this part of the lecture, okay, this part of the class. You probably have never learned this before. The first content is equation of a plane in 3D space. So I need a formula, I need an expression to represent an arbitrarily any plane in 3D space, right? Yeah. So So let's start from something simple at here. So consider that we have 3 points given. Let's call it P1, X1, Y1, Y1, Z1, P2, X2, Y2, Z2, P3, X3, Y3, Z3. So 3 points given in 3D space, and you can try to label the 3 points, right? Let's arbitrarily, let's put the P1 here, and let's put the P2 over here, and let's put the P3 over here. Okay. So once we have the 3 points located in 3D space, okay, then I'll lay down the question now. So the question or the objective, okay, for this part of the question is, what is the plane equation, okay, determined, okay, by the 3 points? Okay. So that's just a legitimate question, right? When you have 3 points given in 3D, and you will be able to draw a plane passing through the 3 points, and you will only draw 1 plane. Right? You cannot have 2 planes. You'll not be able to draw 2 planes, 2 different planes, to pass the same 3 points. Right? So that's basically uniquely determine 1 plane by the 3 P1, P2, P3, as long as they don't overlap each other. Okay? Yeah, 3 different points. So that's the objective. We want to find the plane equation here. Right? So to find the plane equation, here's our approach. Right? So we're probably not going to be able to solve it, but here's our approach. I'm going to draw the plane first, just a sort of illustration that we have a plane here passing through the 3 points. And then to facilitate our derivation, I'm going to construct 2 vectors from P1 to P2, and then from P1 to P3. Okay? I'm going to label the first vector B, label this vector C. Good. Then, essentially now you get it, you know. The plane equation is essentially this plane, right? This is the plane that we're looking for. Right? The plane equation basically means this plane here. Right? This red one. As any questions solving a math question, when you try to find an expression representing generally representing something, right? It's, for example, a line. You know, you have y equal to ax plus b. So that represents a line. And what's involved in the line equation? You have variable x, you have variable y, right? So the variable x and y, you don't give a value, but they are, and you can substitute any values to give you a point on the line, basically. Okay? So for the same purpose, we're going to pick a point on the plane, and then we call the coordinates of this point x, y, z. So basically now I got a P at here with x, y, z. P is on the plane. So the whole idea, the next is to find an expression that includes the x, y, z, which will be the expression for the plane. That's the thoughts here. Okay. Yeah. So how do I find this one here? Right. I think this is where I don't think I have time to finish this portion at here. I will probably finish this in the next lecture. So let's leave it as a question mark here. All right. Yeah. So I'll see you next Monday. All right. Thank you very much.